approaches to studying the solutions of differential equations? Those are the 3 steps in the modeling process. Yeah. Analytical, quantitative, and qualitative. Numerical is the same as quantitative, yeah. So analytical is like solving, you know, just manipulating the variables, solving. Qualitative is when you just think holistically about what the function that has to solve it will look like. Maybe sketching a graph without any precise values. And then the last one is either quantitative or numerical. And quantitative. And we'll see a quantitative or numerical approach in class today. So I kind of gave you part of the solution in number 2, part of the answer to number 1 and number 2. When you use the qualitative approach, is it used to find precise values of the function? No, it's used as a qualitative, what does it look like, big picture. Okay, if you want a precise value, your best bet is analytical. And if you want to get really close to precise value, you could use a quantitative technique. True or false, a parameter is a quantity that does not change with time. True. I should have written false here. False. Okay, so you get a score out of 4 points, 1 point for each question you got right, 1 point for the question you wrote and handed in, and if you took notes, you can give yourself a point to make up for anything you got wrong. Nope. You get it or you don't. Okay, so last class we studied the Malthusian model. Okay, the assumption for the Malthusian model is that populations grow at a rate proportional to the size of the population, which seemed like a reasonable assumption. The larger the population is, the faster it will grow because there are more members of the population reproducing, right? However, when we used that model for the United States population, and we superimposed what the model predicted over the actual population values, it was good until about 1860-ish, really good model, and then the model starts to grow much too fast, much faster than the actual population. So we need to adjust our assumptions about how populations grow. It must not be true that a population always grows at a rate proportional to its size. So here's our second model where we adjust our assumptions. This is called the Logistic Model. It says if the population is small, the rate of growth of the population is proportional to its size. So that is, the Malthusian model is correct when the population is small. Okay. If the population gets larger, if it gets too large to be supported by its environment, right, because there are limited amounts of space, food, water, other resources, then the population will decrease. So that is, the rate of growth is negative. All right, so we have to come up with the variables and parameters that are in play here. So because of assumption 1, we have all the same variables and parameters from the Malthusian model, right? So we had P will be population, T will be time, we had a K parameter. This is the constant of proportionality. And then dp dt represented the rate of change of the population. You can use whatever notation you want for derivative. Okay, so that covers all of assumption 1. Now assumption 2, we have this new thing where the size of the population, there's some size of the population that is too large, right? And under that circumstance, the rate of growth becomes negative. So we still have a variable for rate of growth, so I don't have to introduce a new one, but there's this too large number. Okay, so we have to decide what is too large. So we'll give that a parameter name. For different populations in different spaces, it's going to change. It will be different, but it'll be some value, and we'll call it n, and we'll call that thing the carrying capacity. So in every modeling problem, n is a parameter that you have to figure out what it is. What is the carrying capacity for this population in this environment? All right, so now we're going to try to write an equation that captures the two assumptions using these variables and parameters. So assumption one, we already know how to write something that will capture assumption one. That's the Malthusian model, dp dt is equal to k times p. But then I need that growth rate to be negative. So right now it's always positive because the population size is always positive. K is a positive parameter. So right now, the way I've written this, the rate of growth is always going to be positive. I need to somehow make this thing become negative if the population size gets too big. If the population is bigger than n. So if p is bigger than n, I need that thing to become negative. So an easy way to make this thing negative would be to multiply by one more thing that's negative, right? If that thing were negative, this whole rate of growth would be negative. Okay, so that something can only be negative when the population is big enough, though. If the population is bigger than the carrying capacity, I need this something to be negative. Otherwise, I need this something to be very close to what? 1. Yeah, because I need it to be very close to 1 so that when the population is small, dp dt is basically k times p. Does that make sense? All right, so I'm trying to come up with something to put in there that when p is small, is very close to 1, and when p is bigger than n, is negative. Yeah. 1 minus p over n. Let's see if that fits. K, p, 1 minus p over n. Okay, so if p is very small, then p over n is going to be some small value, something close to 0, if p is small, which means that this quantity in parentheses will be close to 1. If p is bigger than n is, p is bigger than n, then that fraction is going to be what? Larger than 1, right? If p is bigger than n, p over n would be bigger than 1. So 1 minus something bigger than 1 would be negative. Okay, so this fits the bill. It's close to 1 when p is small, and it's negative when p is big. So there is our logistic model. All right, so now the idea is we want to solve it, right? What function p satisfies that equation so that its derivative is equal to a constant times the function itself times 1 minus p over n. So this one is trickier to solve. You can't just do it in your head. We'll learn an analytic technique next class. But for today, we're just going to look at the solutions qualitatively. Without coming up with a formula, we're going to be able to draw what it looks like. Okay, so I'm going to start by looking for equilibrium solutions. Equilibrium solutions are constant functions that satisfy a differential equation. So I'm looking for population sizes that create a rate of growth of 0. Right? So what size population makes dp dt 0? Meaning the population will stay at that constant size forever. Okay. So if I want a constant solution, I need dp dt to be 0. Right? I need the rate of change of the population size to be 0. So I'm going to set kp k times p times 1 minus p over n needs to be equal to 0. All right, so k is a positive constant, so I can just divide that out. Divide both sides by k and it goes away. So now, happily, this is already factored, right? Either p equals 0 or 1 minus p over n equals 0. So p equals 0 means that the population size as a function of time is just always 0. Right? If there are no members of the population, it cannot grow. So that is my first equilibrium solution. Okay, and then this one, I would say p over n has to equal 1, which means p has to equal n. So p of t equals n is another constant solution. If the population size is exactly the carrying capacity of the environment, the population size will never change. That make sense? Right, so I have two equilibrium solutions, 0 and n. So if I was going to sketch what my solutions look like, I have two possible solutions where the population size never changes. So here's t, here's p. So here's one of my equilibrium solutions at 0. My other equilibrium solution is at some carrying capacity n. So what do you think happens if you start with some positive number, some number of members of the population? What do you think happens to the population if you started with, say, 5 members? Yeah, so the Malthusian model says that it's going to at first grow quickly, right? It's first going to grow in proportion to its size. So it's first going to look like that, just like the US population did. But then the carrying capacity, right, is like a limit. You can't get bigger than the carrying capacity. So we've got this asymptote. Right? And if I start very near the carrying capacity, right, it might just grow like that. It might not have a really fast period of time where it grows quickly because it's too close. What do you think happens if you start above the carrying capacity? Say we introduce an animal to an island and we put too many there immediately. It's just going to decrease and come down to the carrying capacity. Will it go below the carrying capacity? So at this point, we haven't taken into account any sort of negative reasons that the population might not thrive. All we're looking at is how quickly it reproduces and how many members the environment can support. If we were looking at, say, predators, which we will in a minute, it might dip down below the carrying capacity. Exactly. Yeah. So our assumptions can't model things like wars, right? Or forest fires, right? If we were looking at a population of rabbits or something, right? So these are very simple assumptions so far. So qualitatively, we can see what solutions to this thing look like. There are lots of possible solutions. These are all functions p of t that would satisfy the assumptions of our model. To find equations for these purple lines, you'll have to wait till next class. But at least we know what they look like. So we know quite a lot about the solutions to this differential equation. without even having to find an analytic solution. Okay, so next we're going to adjust our assumptions about how populations grow again, adding another important variable. This time we're going to look at a predator-prey system. Okay. So we call the prey rabbits and the predators foxes, and since each population influences the other, we have to try to model both of them at the same time. So we have to write an equation for each population. So here are our assumptions, a little bit more complicated. In our first model, we had one assumption. Second model, we had two assumptions. Now we're going to have 4 assumptions to take into account this predator-prey. Okay, if no foxes are present, the rabbits reproduce at a rate proportional to their population, and they are not affected by overcrowding. That's a simple Malthusian model, okay, when no foxes are present. The foxes eat the rabbits, and the rate at which the rabbits are eaten is proportional to the rate at which the foxes and rabbits interact. Okay, so we need to know how often they see each other to figure out how often the rabbits get eaten. Without rabbits to eat, the fox population declines at a rate proportional to itself. So that's almost the Malthusian model, except instead of growing at a rate proportional to itself, it declines at a rate proportional to itself because it has no food. And the rate at which foxes are born is proportional to the number of rabbits eaten by foxes, which, by the second assumption, is proportional to the rate at which the foxes and rabbits interact. Okay, so the birth rate of the foxes depends on how many rabbits they get to eat, which depends on how often they interact. All right, so we're going to try to translate these into a model. We're going to choose variable and parameters as we go. So let's just start with, we'll have R be rabbits. Start with the most basic. F will be foxes. dr dt and df dt will be the rate of change of the size of those populations respectively. So t will be time. Okay, so let's go assumption by assumption and see what other variables and parameters need to be introduced. No foxes are present. The rabbits reproduce at a rate proportional to their population. So we need some constant of proportionality there. So let's have that be alpha. We'll just use Greek letters. Each time we introduce a new parameter, we'll move up a letter. So I'll put alpha there. The foxes eat the rabbits, and the rate at which the rabbits are eaten is proportional to the rate at which the foxes and rabbits interact. So we need another constant of proportionality for this one. We'll call that one beta. Without rabbits to eat, the fox population declines at a rate proportional to itself. We need a constant of proportionality there. We use gamma. And the rate at which foxes are born is proportional to, so we need a constant of proportionality for that one, gamma delta. So I've got 4 constants of proportionality in there. All right, so now I'm going to try to put these together into an equation. Right, so 2 equations. I need an equation that models the rabbit population, an equation that models the fox population. Okay, so let's look at the first assumption. No foxes are present. The rabbits reproduce at a rate proportional to their population. So this is the Malthusian model. So dr dt would just be alpha r, constant of proportionality times the size of the rabbit population. Foxes eat rabbits, and the rate at which the rabbits are eaten is proportional to the rate at which the foxes and rabbits interact. So One way that we can model how often rabbits and foxes interact is to multiply the size of the rabbit population times the size of the fox population. As each one gets bigger, they will interact more often. So if you multiply them, we can get some sort of some number that will tell us how often they interact. Okay, and the constant of proportionality will scale it appropriately. So as R gets bigger, the number that measures how often they interact needs to get bigger. And as F gets bigger, the number that measures how often they interact has to also get bigger. Yeah, there's more than one way that we could come up with a number that measures how often they interact. Yeah. So one common way is to just multiply the two populations together because it does qualitatively do what we want it to do. Right? As one population gets bigger, one or the other or both gets bigger, that number that models how often they interact has to get bigger. As one or the other gets smaller or both get smaller, that number that models how often they interact has to get smaller. So the product of the two population sizes captures that. So dRdt, it grows proportional to its size, right? But then there's also this thing where rabbits get eaten, right? So that would decrease the rate of growth of the population. So I'm going to subtract from that the rate at which the rabbits are eaten, right? And I'm going to use R times F to measure how often they interact, and gamma was the constant of proportionality. It was beta, you're right, sorry. Okay, so now that you know the trick about R times F, let's see if we can come up with dF dt. So using this first bullet, without rabbits to eat, the fox population declines at a rate proportional to itself. So how do I write that part of dF dt? Gamma, we just used beta, yeah. Yeah, gamma F. And we could assume gamma is positive and then we'd have to put a negative sign in front, or we could just write in our assumption that gamma has to be negative. I don't remember which one your book does. It assumes all the parameters are positive, so we have to throw a negative there. Because that, it declines at a rate proportional to itself. So in order to have dF dt negative, we've got to throw a negative there. It wouldn't matter because if R or F were 0, doesn't matter what the constant of proportionality is, you'll still get 0. Yes, plus, right? And then the fox population goes up with more interaction, right? So that's why we have the plus there. And then R times F is the interaction number, and then delta is the constant of proportionality. So here we have two equations. R and F depend on each other, so we would have to solve this thing simultaneously to figure out the rabbit and fox population formulas. So this pair of equations is called a first order system. First order because it only has first derivatives, and it's a system because it is two equations with two unknowns. The solution to this first order system is a pair of functions, one for rabbits and one for foxes. And since the two functions depend on each other, you can't just solve one and then solve the other, right? Because as rabbits change, that affects the foxes, and as foxes change, that affects the rabbits. So you have to solve the two equations simultaneously. And it turns out that there's no simple analytic way to do that. Okay? for most values of the parameters. So we're going to have to either use a qualitative technique or a numerical method to study the solutions. Okay, so one way to study a solution numerically is to pick initial values for R and F. Okay, so we could just say we have some island where we put 12 rabbits and 2 foxes on the island, right? We could assume some starting values, right? And then dr dt and df dt tell you how fast or slow those populations are changing. So you can use dr dt and df dt because you know how those tell you how fast the populations are changing. You can use that rate of growth to predict what's going to happen at, say, 1 day later or 1 year later or whatever our units of time are. So let's look at our model that we wrote. We're going to take all the parameters to just be 1, just to simplify, get rid of the alpha, beta, gamma, and delta. And we'll say dr dt is r minus rf, and df dt is negative f plus rf. Okay, so I want to look at time 0 here, just time 0. So r prime, it's a little bit handier to use the prime notation to say at time 0. The derivative, the rate of change of the rabbit population at time 0, we have 12 rabbits and 2 foxes. So I can just plug into this formula. Replace my r with a 12 and my f with a 2. And so when there are 12 rabbits and 2 foxes, the rate of change of the rabbit population is negative 12. Say rabbits per time unit. I didn't give the time units, I'm sorry. Per unit of time. So the rabbit population would be decreasing. 12 rabbits, 2 foxes, the rabbit population is going to decrease by 12 rabbits every unit of time. What's going to happen to the fox population? So we're going to have negative 2, right? Plus r times f, which is 12 times 2. That's 22 foxes per time unit. Right? So that's how fast the fox population is changing. It's going to be growing by 22 foxes every unit of time. So that way, I can now predict r of 1 and f of 1, right? The size of the rabbit population and the size of the fox population 1 unit of time later. So rabbits started with 12, and they're decreasing by 12 rabbits for every unit of time. So 1 unit of time later, how many rabbits are there going to be? 0. Yeah, starting with 12, going down by 12 every unit of time. 1 unit of time later, there will be 0 rabbits. And foxes started with 2, and they're increasing by 22 foxes per unit of time. How many are they going to have 1 unit of time later? 24. So we now can use numbers to predict, right? And I could repeat this again. I could now calculate r prime of 1 and f prime of 1 using my new values of r and f in the formula, and I could predict the values at 2, at time 2. It'll still be 0, yeah, for rabbits because they're gone, yeah. And foxes will probably decline because there are no rabbits to eat. Yeah. So this is a numerical method, right? So I could do this again. I would do r prime of 1, and my formula would be 0 minus 0 times 24. The rabbit population is not changing. And then my fox population, f prime of 1, plugging in my values of f and r at 1 now, would be negative 24 plus 0 times 24 is negative 24. Say that again. I just don't know what you're asking me. Say it again. Okay. The way I calculated R of 1 is I looked at R of 0. I looked at how many rabbits were there when I started, which was 12, right? And then I looked at how is it changing. Every unit of time, it's going down by 12 rabbits. So 1 unit of time later, that's the 1, right? I said we started with 12 and we're declining by 12 rabbits, 0. So I'm using the rate of change to calculate the value of the function 1 unit of time later. It's still an estimate because the rate of change doesn't stay constant for a whole unit of time. The rate of change is changing. But yep. So now that I know R prime and F prime at 1, I can predict R of 2, right? Well, at 1, I had 0 rabbits. My rate of change is 0, so I still have 0 rabbits. And my fox population at 2 units of time, well, I started with 24 rabbits. The rate of, foxes. I started with 24 foxes. The rate of change for the fox population is now declining at 24 foxes per unit of time. So how many foxes do I have 1 unit of time later? 0. So both populations died out. So if you put 12 rabbits and 2 foxes on an island, this model predicts that both will become extinct within 2 units of time. Okay, so this is a very long process. This computing numerically what happens at each unit of time. A computer program is really helpful here. Just program it to calculate dr/dt and add it to the previous value you had. We'll get way more into a numerical method next week. So we've seen 3 models now, the Malthusian model, the logistic model, and the predator-prey model, and 3 techniques for studying the solutions of a differential equation. An analytic method, where we could at least check that a function is a solution. If it's simple enough, we were able to sort of brainstorm what a solution could be. Qualitative, where we can sketch solutions without finding a formula. And numerical, what we just did. So the next 3 sections of the text are going to further illuminate those 3 techniques. So we'll spend the next 3 classes doing a numerical, a qualitative, and a quantitative technique. All right, so your class activities is to practice modeling. Given some assumptions, write a model.